Here is a question that I'd like you to keep in mind as you go through the video. The residuals in a logistic regression are normally distributed just like those in a linear regression. Is the statement true or false? The relationship between logistic and linear regression is a subtle and also an important one because the way in which we will solve logistic regression in TensorFlow will be quite subtly similar to that in which we solve linear regression. So let's make sure that we understand it. Recall that linear regression is all about attributing effects to causes. So X causes Y. This is the kind of relationship that we want to quantify with linear regression. We have causatory or independent variables, and we have effect or dependent variables. And the relationship between X and Y is defined in the form of a straight line. Given a set of points, linear regression then involves finding the best fitting line which passes through those points. And the word best here has to do with a certain error metric, that is the mean square error, or the square of the lengths of all of these residual dashed lines. This is how linear regression works. We need to find the best fitting line. Y is equal to a plus bx. Logistic regression is actually very similar. Logistic regression is all about predicting probability. So on the y-axis, we have the probability of y. Also, we have the actual observed values of y. These can only be 0 or 1 for a binary variable. This means that we now have a set of points which will lie along the line y is equal to 1 and another set of points where y is equal to 0. The logistic regression process is very similar to the linear regression process. It involves finding the best fitting S-curve rather than the best fitting straight line. This is the S-curve which will pass through all of these points and which will best model the probabilities of y being equal to 1 using the S-curve equation that we see on screen now. And that process, that algorithm of finding that best fitting S-curve, involves finding the best values of A and B. Clearly, there are a bunch of similarities and differences between logistic and linear regression, so let's quantify them by placing them side by side. Linear regression focuses on predicting effects given causes. That means that given the value of the x variable, what we are looking to do is to predict the value of the y variable, and we do so by using a straight line. Logistic regression is looking to predict the probabilities of effects given the causes. So this time on the y-axis, we are going to represent not y itself, but rather the probability that y is equal to 1. By the way, for this two-dimensional example, we are just assuming that y is a binary variable in the logistic regression case. From the examples we've already seen, it's pretty clear that linear regression needs the effect variable y to be continuous. In logistic regression, on the other hand, the effect variable must be categorical. It must be drawn from a finite set of outcomes. The causatory variables can be either continuous or categorical, and this is true with both linear and logistic regression. So in neither case is there any restriction on the type of variable used as the explanatory variable. Given the differing natures of the y variables, in linear regression we seek to connect the dots with a straight line. In logistic regression, we seek to connect the dots with an S-curve. And we've seen why S-curves are a good fit. They model reality pretty well in a lot of their use cases. In both cases, the functional forms of the curves that we are trying to fit have been decided up front. In linear regression, it's y is equal to a plus bx. In logistic regression, it has the probability of y on the left-hand side and that S-curve, the exponent, on the right. The functional forms are different, but the objectives of the regression algorithms are the same. In both cases, the objective of the regression is to find the values of A and B that best fit the data. And now there is also a special relationship between linear and logistic regression. The linear regression equation is linear by assumption, by definition, in fact. The logistic regression equation can be made linear by taking something known as the log of the odds. This is a log transformation which allows us to change logistic regression into a linear regression problem. Please focus on this equation now on the right. The point and the importance of this equation is that we can now solve logistic regression much as we would solve a linear regression problem. There are a whole bunch of cookie cutter techniques which exist to do this. We don't really need to prove this mathematically, but I feel that it's important enough for us to understand exactly how we get here. So let's start with the logistic regression equation. Here we have found the values of A and B that best fit our data. And we have used these to define an S-curve where on the left-hand side of the equal sign, we have the probability that y is equal to 1. And on the right, we have the S-curve, that's the exponent. Let's just abbreviate that probability. Let's just call it P for short. That is the probability that y is equal to 1. Now, if you're familiar with the definition of the odds of an event, that is on screen now. The odds of any event with probability P are simply defined as the ratio of P to 1 minus P. The odds of an event are a really popular way of expressing its probabilities. There are lots of folks, particularly in sports betting and gambling, who think intuitively in terms of odds. In any case, let's now keep moving on. Let's calculate the odds given our formula for the probability, which came from the S curve. Here, we started with the probability which was defined by our S curve. And it turns out that this is a formula which lends itself really well to calculating the odds. We get to the denominator of the odds formula, that's the probability of the complementary event. I'd highly recommend that you just jot down these formulae with pencil and paper and work through them. It's much easier than viewing them on screen line by line. But the bottom line is that you will be left with values for P and 1 minus P, which when divided by each other give a really nice formula. The odds of P simply work out to be e raised to the power a plus bx. Now it's simple enough for us to transform this equation by taking logarithms to the base e on both sides of this equation, and we end up with a straight line equation. On the left of this equation is the logit. The logit is used to refer to the log of the odds of any event. And on the right, we are left with a straight line, a plus bx. And this finally is the bottom line. We have been able to reduce our logistic regression S curve into a linear equation relating the logit function on the left to a straight line, a plus bx on the right. And this means that logistic regression can be solved via linear regression on the logit function, the log of the odds function. We will actually not use this method when we are implementing logistic regression in TensorFlow, but this is important background so that you can understand how linear and logistic regression are conceptually linked and why logistic regression is called linear classification. Let's come back now to the question we posed at the start of this video. The residuals in a logistic regression cannot be normally distributed because after all, they represent values from a categorical set. Consider binary classification, for instance. The actual labels are going to be either 0 or 1. The predicted labels can also only be 0 or 1. So the difference between the actual and the predicted labels will be 0 plus 1 or minus 1. This represents a discrete variable, a categorical variable, and this definitely cannot be used to represent a normally distributed variable. A normal distribution looks like a bell curve and it is inherently continuous. So the regression residuals in logistic regression are not normally distributed. This is a difference between linear and logistic regression residuals.